let me just say. Yes, actually it's record as well. Giovanni, I don't have permission to record. That's probably fine. Okay, so I think we should go ahead and start. So good morning, everyone. I'd like to welcome you to this week's invited lecture for the course. And we have Simon Dobnik as guest today. He's a professor at the Department of Philosophy, Linguistics, and Theory of Science at Gothenburg University. Yeah, thanks, Giovanni. I was able to record now. Yeah. Simon got his PhD in computational linguistics from Oxford. He works on computational models of language and perception, human-robot interaction, computational representations of meaning, and among other things. He also teaches in the Language Technology Master at Gothenburg University. And he will tell us about learning language and beyond today. So yeah, the floor is yours, Simon. And it's up to you if you want to take questions during the lecture.
Yeah, it's good. Yeah, people can just either just barge in or type a question.
Yeah. So I think you can just speak up if you have questions. We're not that many participants, or if you keep an eye on the chat as well, maybe.
Yep. Sometimes I miss the chat when I share the screen. So if I miss something, let me know. Yeah.
Okay. Thanks.
Yeah. Thank you very much, Mats and Giovanni, for inviting me to this course and giving a guest lecture. So today, so I work in language technology, and we use machine learning and language technology quite a lot. So this will be like a survey lecture of the main issues that we discuss in language technology, and also how they relate to machine learning, how we solve those problems with machine learning, and what kind of representations and models do we use. So quite a few of these will be the models that you've probably seen before, either in the previous courses or in this courses, but maybe in different contexts. And therefore, I would be very glad if you also, if you see comparisons between the work that you do and the work we do in the language technology, I think those discussions would be also very useful and interesting for this. But generally, as Mats said, just feel free to interrupt at any time, and we can take it, at a pace with questions and also discuss the related questions that you might have. Okay, so let's start. So I'll first say something about natural language processing, kind of what it is and what we do. And then I'll try to summarize very quickly why NLP is hard. What are the main issues that we are trying to solve? And we are trying to solve for a very long time. So NLP has been around since the beginning of computer science. A desire for machines to analyze natural language is one of the things that is important for us. And then, as I said, I'll talk about representations and approaches that we use in NLP, and I'll conclude with some remarks about the future and the current problems that we are working on. So I'll try to present the area from by introducing you to some general points, but also I'll try to kind of add some examples of the problems that our group is currently working on, or we have been working on, and therefore you can also see what we are doing at the moment. All right, so natural language processing. So what do? We write computer programs that behave as if they had some understanding of human language and can produce human language. So you see that I underlined as if. So there is no requirement, or there is no goal to actually to replicate human cognitive processes, but we just want to have the performance of human natural language generation and understanding, right? So these two things are quite different. You use different methods to analyze language, and different methods to generate language. Of course, there will be some parts in common. And in my particular interest is to build artificial agents or robots that interact with us in language. Why would we do that? Well, so understanding and also generating natural language by machines is important to us, right? Because a lot of human knowledge is encoded in natural language, in unstructured text, for example, right? We have a vast amount of human knowledge on the internet. Well, we have Wikipedia, but we have also other sources of knowledge, right? And this knowledge is not in any kind of structured databases that can be easily queried, right? So we need to extract meaning from this information and then use it in our application. So normally we do some reasoning with this information, right? On the other hand, having artificial agents and robots is very useful to us as well. So we want to do we want them to do like meaningful tasks in our homes, and most users won't be expert programmers, for example, right? So a very natural way to program your robot is through instruction in natural language. And so this kind of programming your robot with natural language will again would involve learning from human, adapting to human and the environment in which they are situated. So sometimes the field is called computational linguistics. In fact, the major conference and organization, Association for Computational Linguistics, carries that name. So in Gothenburg, we frequently hear language technology. We also have a master's in language technology. Sometimes people refer to natural language processing. When you mention that, you probably mean more on the methods and algorithms, but language technology is perhaps slightly more general when you also consider how technology is used. Well, all this is part of artificial intelligence because, well, understanding and producing human language is important a part of human intelligence. So language technology, computational linguistics, natural language processing has always been considered as one of the central part of AI. So what is the language technology of the future? Yeah, it's kind of like C3PO, right? Who is fluent in more than 7 million forms of communication and also can translate between all these languages. But well, we don't have to go to the future to see language technology in action. So even today, we are using language technology all the time. For example, when we do even when we type text on our phones, when we have predictive text input or spelling correction, or when we're searching for information on Google, or we can also do more sophisticated things on Google, like question answering, right? That entails interpreting a question and then running some query in the background that this question is resolved to, and then analyzing, finding the documents that contain potential answers, and then extracting information from those documents, right? So the question here was, which countries does the Danube flow through? So Google understood the question, found the relevant documents, and then also connected flow through with runs through. Right, so there is not like a direct keyword that Google found in this document. So it did some meaning comparison, meaning analysis in order to find this question. Another example on Siri, we can ask questions like, what is the distance between Oxford and London? And here Siri gives us an answer. London, England is about 95 kilometers away from Oxford, England by car, or about 84 kilometers as the crow flies. So here, well, the system needed to interpret the question, again, turn it into a query, but the query was then issued on some kind of a geographical database or a map in order to determine the distance, right? So here we have an example where reasoning is not, let's say, meaning comparison, semantic comparison, but some kind of other reasoning, geometric reasoning that was required to establish the distance between the two cities. Yeah, so that's the NLP. But why is it hard? Why we haven't got like robots around us in everyday lives and interacting with us, right? Or why do we sometimes get really bizarre results when we type in things on Google, or we have conversations with conversational agents that really don't take off, that are very unnatural, right? So what goes wrong, and why is it challenging? So first we need to figure out what do words mean. So if we take this example, like a textbook example, Francis saw a stranger with a telescope. So we need to, well, we need to relate words like Francis saw to some other representation. Like as you saw previously, this could be either information that we collected in our documents in the Google question answering example, or some other geometrical and reasoning with the geometry and space in terms of the spatial query, right? So let's say we find a way to associate Francis with individuals that have the property of being Francis, or saw with some actions. So we need some access to some other reality. Well, we need access to our reality, really. And the other thing is, it looks like the words, we need to find the meaning then composes. Like, you know, humans have intuition what Francis saw refers to, right? What kind of situations would Francis saw refer to, right? And the whole sentence refers to some situation, namely Francis seeing a stranger with a telescope, right? So how do we relate the words with some other representations of the world or reality or a database? Yeah, so language is not just a sequence of words or sounds. Like here we see a sequence of words. But in order, when we want to do an analysis, what these words mean and how they relate to each other, they really form a graph like this, or a tree, right? Because some units in this sentence are more closely connected than others. Like Francis saw a stranger with a telescope. So, for example, we can replace a stranger with another person's name, or another individual, right? Or another description. Francis saw a person with an umbrella. For that, we can replace stranger with that, right? And we have this intuition that with a telescope is relating to a stranger, right? So that's why we mark this dependency here, right? So, and that kind of makes the task very challenging, because you need to, from a linear sequence of words, you need to figure out these graph dependencies between the words. But it gets more complicated than that, because a single string can sometimes turn into, well, actually most of the times can turn into several graph dependencies that all make sense to us, right? So here we have one of those analyses of the sentence, namely we chose to attach with a telescope to a stranger. So that would, we would interpret this that a stranger was carrying a telescope, right? Because this is link to a stranger, right? But of course, with the telescope can also be attached to the mode of seeing, right? So here, Francis was using a telescope to see a stranger, right? And language is ambiguous. And kind of the argument for that is that this is due to communication economy. So we don't really need to say everything we mean. We let to the other person to figure out what we mean. And this lets us to be more economical, right? Because in a single string, we can actually express these two meanings at the same time without, you know, in a compressed sense, perhaps, and then let the other person figure out which of those analyses we meant, right? But this ambiguity is not just it's not just syntactic, it's also semantic. Or actually, we can build such graph dependency between, not just between words, but subwords and also sound, letters or sounds, if you wish, and also meaning, right? So, so here also, but also lexical meaning, like Francis could be he or she, right? So again, this is underspecified in terms of the gender, and again, that needs to be that humans just let this to other communicative partners to figure out what is meant by he or she. But wait, it's more, because this kind of proliferates when we talk to each other, right? And then we get into conversations like this. Okay, so I see a red mug directly behind the red one on your left. That's probably next to the white with funny top that I can see. And then the other person says, P1 says, it is just behind that and to my left, you're right. Behind from my perspective. Now, what happens here? So we have, we first of all, you see that sentences are not like very nice sentences with a full stop at the end, right? So in spoken language, in communication, you get a lot of variation. You get incomplete sentences, restarts, interruptions, continuations. So that is one of the problems. The other problem is that person P2 and P1, they are referring from their perspective as speakers, right? So they use things like my and your, but that the kind of the interpretation of that is related to who is speaking, right? And yeah, so what happens is that in human interaction, human communicators try to, well, I forgot to say, okay, so there's lots of mess here, but what is then, but how do we understand each other, right? And the reason for this is that when we talk to each other, we really want to achieve common ground, right? And common ground is mutual knowledge and shared beliefs. So of course, we cannot access each other's representations of common ground because those are in our heads, right? But then when we talk to each other, we constantly monitor each other and try to monitor what we agreed so far, right? And we also use like methods like confirmations that I just used now. And we also built a theory of mind. So we are able to represent other beliefs, desires, and intentions. So when I communicate, I adapt my sentences to the beliefs of the others, for example, right? In order to achieve common ground. And then the third kind of element is that when we communicate, we have some joint goal and we are cooperative because we have a shared intentionality. That's kind of the purpose why we talk to each other. We are trying to solve some goal. In this case, two participants are trying to find mugs on the table, right? So we gave them a task where they see slightly different scene and a table with lots of cups, but some of the cups are missing for each, and the task for them is to find those mugs, so that is their communicative goal, and they kind of adopt different strategies and generate language you know, that fulfills that goal. So the language will then be dependent on what the goal is, right? So it's a very creative usage, but also creates a lot of variation, right? Now, the third thing that we need to consider is, like, if you read this conversation here, probably wouldn't understand what is going on. I mean, you would understand that it is something about finding mugs, but really visualizing what they are saying would be very hard, right? So this dialogue was collected when participants were seeing a scene with the mugs. So really, to understand language, we need to connect it to the world, right? And so to other representations. For example, here is a scene from experiments with learning language from robots, and we want the robot, so the robot was learning instructions like this from human instructions, from human descriptions: turn right at the table and stop at the chest that is close to the stack of tiles, right? So this robot needs to then learn how to relate words or the whole descriptions to representations, geometric representations that it has created with their sensors. In this case, we were using SLAM maps, which SLAM stands for simultaneous localization and map building, and that gives you point cloud representations of the scene. And it had to relate those words to the geometry of those point clouds and the labels we gave to separate parts of the point cloud. I'm just checking if there are any questions. So please do interrupt, or if I'm going too fast, let me know. Yeah. So, relating it to reality is a bit more complicated than just finding geometry of the room and representing that. So here we have an example of image captions. So these descriptions were generated by humans using crowdsourcing, Amazon Mechanical Turk, and each description was produced by a different participant, right? And as you can see, the first participant described a big black brown dog plays outdoors. A black and tan dog leaps over the green grass. A brown and black dog runs on the grass outdoors in front of a sidewalk. Somebody just said a dog runs, or a German shepherd jumps left on the patchy grass. So a couple of things notice. We are particularly interested in these descriptions that describe space, like over, right, or on. And what does on mean and over, right? So if you consider the geometry of the scene, and also like this picture, how on looks like, it's very different on than, you know, a cup is on the table, for example, right? So these two geometries would be completely different if we represent them computationally. The other thing is that notice that the different participants describe the scene quite differently. Somebody said a big black and brown dog, a black and tan dog. So there is some kind of difference in color, like brown and tan. In this case, either the beliefs of participants are different, or the brown and tan actually refers to the same color, which might not refer in other cases. Then also how the dog is described. So sometimes it's just a dog, sometimes it's a dog with a particular color, and sometimes it's a German shepherd, right? So here, I guess it's because kind of this intent, what the person knows, what they want to emphasize, what their background knowledge is. So this is kind of the information that participants are bringing in from the outside, externally. There's nothing in the image that tells us about this, right? And the other thing is, like, what does it mean to run or jump over? Because in the scene, we just see a static scene, right? But in reality, as humans, we are kind of able to do some kind of a mental simulation to predict that the dog is running or jumping over, right? Or jumping left. So we kind of have to, we are very good at estimating what's going to happen from this picture, right? But a machine would just have pixels, and from the position of this body, it would need to determine that this is jumping rather than falling, for example, right? Yeah, and the other thing is what we were also interested in, and which actually came out from these experiments with the robots, is that we take the spatial perspective as well. Well, like my left is your right, or somebody else's front. So how do we do that? Because, you know, here a person just said left, right? But from the dog's perspective, it's jumping right? So, but we never said whose perspective to take. So how do we kind of figure out which perspective to describe the scene from, and without actually saying, oh, from where I stand or from my perspective, this is left, but of course this is your right. And again, a communication like this would be super boring. Now, imagine with all these problems, now you want to build, well, you want to use a machine learning classification or prediction to understand or generate these descriptions. So as you see, there is the kind of the problem is that there's a huge variation of the description, and but of course not every description goes for this scene. So there is also some quite strong restrictions, right? Not all information might be directly expressed in the source that we are classifying, like the image here, right? Like, how do we know that the dog is jumping? We don't have all the information from the dog's joints to generate to predict that the dog is jumping, right? And kind of the final thing that is challenging also here is a lack of data, because well, you know, taking pictures is or sensory scans or is easy because, you know, you get plenty of information every second, but getting humans to describe these scenes is time consuming and also expensive, because you pay for them on the mechanical Turk. And since the language is kind of contextually dependent, you would have to kind of collect data from all sorts of different contexts to really have generalizations that you want, right? So there's a lot of data around, but still not enough data to kind of to make. Well, it's getting better, but we're still not there. Yeah. Okay, so that's, I hope I kind of convince you that doing NLP is worthwhile and interesting and exciting, but also challenging, right? Now, let's look at some representations and approaches that we use to do that. And we start from the distributional hypothesis of lexical meaning. I'm just checking the time. And so how do we represent meaning of words? So this goes back in the 50s of the previous century. And there was a distributional hypothesis of lexical meaning was suggested. Namely, that the meaning of a word is the set of contexts in which it occurs. Or a slightly weaker version of this hypothesis is that, well, it's not actually the meaning, but important aspects of the meaning of a word are a function or can be approximated by the set of context in which it occurs in texts, right? So let's see how this works. So if I present you the first sentence, he filled the vampimuk, passed it around, and we all drank some, right? What do you think vampimuk means there? Could somebody have a guess?
Cup.
Right, yeah. And in the second case, we found a little hairy Wampimuk sleeping behind the tree. So in that case, probably Wampimuk is an animal, right? But how do we know that? We simply know this by seeing what other words are around this word, right? And this is what we mean by context, right? So we can approximate the meaning of the words by considering other words around, and the same for other words, like, sleeping would have other context, including Wampimuk, if this wouldn't be a made-up word, right? That people introduced it in the literature. No, I think it's just a made-up word from one of the papers. Yeah, yeah. So the idea is, yeah, you can make up a word that doesn't have a sense at all, you would be able to guess what it means. And again, as you said, the same works for a lot of the vocabulary from Harry Potter. And I think the success of that vocabulary is that people can usually guess what those things would be, even though if they haven't heard these words before. So what do we do then? We collect a corpus of text. Now it's important that this corpus of text is large enough and balanced enough, and contains the words that we want to model, because if the word won't be there, we won't be able to make any predictions. And then we represent the contexts. So these are the words around that word as columns in this matrix, right? So each representation of a word will then be a vector like this with the counts over these contexts. So that means that dog occurs with leash 3 times and walk 5 times in its context. And cat never occurs with the leash, and it occurs with run 3 times and so on. But car only occurs with run once and 3 times with owner, right? From this, we can say actually that dog and cat are very similar if we just compare these vectors, right? But dog and cat are different from a car. But we can also say that in the dimension of the owner, all 3 are very similar, right? So this is like the comparisons that we can make. And so one of the problems here is that this will create a sparse matrix. And so these are normally called sparse representations, right? Because there'll be some dimensions that don't have any, that have lots of zeros in, right? So what we can do is...
Sorry, I just have a quick question.
Yep.
How do you define the context? Like, is it within the same sentence or within the same paragraph, or like, where does the context end? So you know how many times, like how you should count them, prepare them.
Yep, that's a very good question. Thank you. Yeah. So it depends on what you want to do, actually, right? So there's been work and has shown that increasing the context to, normally it's like 5 or 3 words left and right, but if you increase the context to documents, then you get obviously different counts, and so you get more like, if the context is very narrow, you get more like what we call more low-level semantic representations, like these kind of associations. Even making the context very narrow, you would get almost like some syntactic relations, like as well, like verbs and auxiliaries are occurring together, right? But if you widen the context, then you get more like topics of documents, right? So that's normally it's a kind of an empirical decision, but when tests have been done, they have shown actually that those vector spaces, those representations are actually encoding quite a different linguistic knowledge. Yeah. Yeah, that was a really good question. Any more questions at this point? Okay, I will just continue. So what because this is counts are obviously not good, because so depends also on how frequent that word is, right? So some words are more frequent than others. Then what we can do then, we can use measures that penalize frequent words across all contexts, right? So you might have heard TF-IDF from information retrieval, term frequency, inverse document frequency, and positive pointwise mutual information. So these are like two measures that penalize frequent words across all contexts. So pointwise mutual information is the product of the probabilities of these words occurring together divided by the product of occurring them individually. So it's always it's also called log likelihood ratio, right? So you kind of integrate that aspect in the values that you present in your matrix. We can also then start going from the raw counts or raw TF-IDF scores or PPMIs to reducing the dimension of this matrix, right? So that is known as latent semantic analysis, and the method to do that is called a singular value decomposition. So you end up with much smaller matrix that you started in, and you remove all those all the matrix sparsity, right? And this is kind of on a way towards more dense representations that we're going to see in a minute. And then once we have meaning representations, or maybe, a related question to what counts as a context is also, people also discussed a lot, what kind of words should we include in context? Should we leave out words that are frequent words like determiners and auxiliary verbs and so on? And again, I think the opinion is different. Sometimes the determiners are actually helpful to know that, determiner is your context, then that word is a noun, not a verb. Like some words in English can be both nouns and verbs, like can, right? So auxiliary verb or a can of fish, right? Once we have these vectors, then we can do interesting things with them. For example, we can compare them. We can compare them with. We measure similarity with cosine similarity, right? So purely from the practical reasons, because cosine of 0, which is the identical vector, is 1, right? And therefore, the 90-degree vector would be 0, right? So, but so cosine similarity is used to estimate, to compare these vectors. Then it has been pointed out in the literature when such vectors were evaluated, they also, I forgot to mention, we evaluate, let's say, the cosine similarity between these two vectors with human similarity, like we say how similar dog and cat are, and then we collect judgments from participants, and from 1 to 7, let's say, and they say 6, or we get the average of them, and then we compare the cosine similarity with that. We calculate a correlation between the two lists of scores. But then the other way to compare knowledge encoded by these vectors is to do vector subtraction and sum, right? So it has been shown that if you do these word analogy tests, like you take the vector for king, you subtract the vector for man, you add the vector for woman, you get queen, right? You can do the same by Paris is to France as Stockholm is to, and you will get a similar vector to Sweden, right? So if you're interested in these, so these are kind of some classical the textbook papers when they discuss these questions in more detail. But what is surprising is actually that these vectors show not just like semantic meaning, but also a lot of information about the world, which is semantic meaning, and it's quite surprising that kind of inference like this actually works quite successfully. And this is kind of the dominant way, the way we represent meaning in NLP. So in most of the cases, then we don't have access to the real situations. We only have access to text, and therefore we extract the meaning intrinsically from the text, right? Not directly observing situations in the world. Okay, I'm just trying to check. Okay, we have a couple of more minutes before a break. So then let's look at now at the distributed meaning. So so before we said these are sparse representations because they are matrices of raw counts. But we can also use machine learning to learn representations, to learn these vectors, right? And the most important paper in this for this idea is the paper by Benjo from 2003. And later on, the idea has been taken on by Mikolov from the Google team, and who developed word2vec, which is today even today is like one of the most important vector representations for words, for lexical words, right? Word embeddings, they are called. So what do? Okay, so we train a neural network where the inputs are the inputs are the context words. So the word that we try to predict the target word, right? And the context will be the inputs will be our context words, right? So this will be previous word, 2 previous words, and so on, depending on how large the context will be. And then we create we learn a hidden layer in between, and take a softmax over it so that all of them sum to 1, and then predict the target word, right? And as a vector representation, we take the hidden layer or the softmax here. So in that case, then later on when we apply this model, we simply we train it on lots of text, and then if we want to have the vector for a particular word, we take their context and try to and then take that representation, that softmax layer here, as our vector representation of that word, right? Yeah, so there's a couple of things I have not mentioned. So these are called, dense representations, because we have learned the representations rather than directly representing them, or word embeddings. We learn them intrinsically from the text. You might ask, so how do we encode words in a neural network? So we use one-hot encoding, where it's simply a vector where one of the values is 1 and the rest are 0. So these typically will be very large, and they would correspond, the length of that will correspond to our vocabulary size. And then this hidden layer in between should have a reduced dimensionality. And in the Mikolov paper, they experiment with 300 or 600 dimensions for the hidden layer in between. So these will be the length of our vectors, or the reduced dimensions of those words. And we have, actually, there are 2 models that Benjo and Mikolov implement. One is the CBAO, or continuous bag of words. So this is the one that I've just shown you on the previous slide, where you start from the context to the target word. But you can also train the network in the other way around. So you start with the target word, and you predict the context words on the other side out, right? So both of them work, and kind of what they have in common is that this hidden layer, or layers that they learn with reduced dimensionality, and these will be then representations for that word. One important thing here is that we introduced the notion of pre-training, which is now used in NLP and computer vision a lot, right? So we train these word embeddings, and then we save the model, and then we use it as a feature encoder for another task. So you know, we train our word-to-vec model, and then we just use it like that for another input to another neuron, to encode information as input to another neural network that we want to build, right? So the idea is this, that we encode the semantic knowledge in this network, pre-train it on large quantities of text that we couldn't possibly collect for this task, but then we hope that these representations would also be useful for another task that we are doing, right? So here I have two links to word2vec in TensorFlow, and also how to build word embeddings in PyTorch from scratch. Or, as I said, you can also download the pre-trained model already and start from that. Yeah. So maybe just before the break, let me do this slide. So, yeah, so these representations tell us a lot about the world. That's because there are situations in the world, those are reflected in descriptions of situations, and these descriptions of situations are then mapped to distributed representations, right? But these are disconnected from the world, as I said, right? And you might have heard about the Chinese room experiment or argument by philosopher Searle, who argues, you know, that machines will never understand language precisely because they are disconnected from the world. So it's like somebody would be in a room and they have a dictionary, and they simply, you know, and somebody's passing in information into that room in English, and they have a dictionary and they know how to translate it to Chinese. That person in the room would never have an experience of the world and would not understand what language is, right? Yeah, but as I said, we use them all the time in NLP, and they're useful for things like general reasoning, like the sun rises in the east. You know, because we can collect data from a corpus, and if sun rises and east are associated a lot of times, then we can say that this is maybe true, right? Or we can say something about the sentence. Similarly, like Gothenburg is situated by Kattegat on the west coast of Sweden, and has a population of approximately 570,000 in the city center. Could also be inferred from the text just by observing the association between these words very frequently, right? But we get into trouble if we want to infer, well, is the chair to the left of the table, right? Or is the chair to the right of the table? Because in this case, both left and right have completely the same context, right? So that would give us exactly the same vectors, really. And we cannot really infer anything about spatial reasoning from this example, right? And well, as I said, this kind of approach to representing meaning in NLP has been very successful, but there's been a lot of discussion recently whether we have reached the limits of NLP doing it this way, right? And if you're interested in this question, I suggest you have a look at this paper here that I also, I think, included in the lecture announcement by Bender and Koller, and when they're also suggesting where to go next and what kind of questions the NLP should ask. But I think we'll kind of return these after the break. Yeah. So if you maybe if you have any questions, quick questions, otherwise I suggest we take a 15-minute break now, and we can be back at 6.